Alright, welcome back to IDIS 343. Now we're starting a brand new topic, Chapter 5, the transportation problem. Here's the plan. First, we'll define what the transportation problem actually is, basically moving goods from plants to warehouses at the lowest cost. Then we'll try a greedy heuristic, like a quick common sense rule, and see where it gets us. After that, we'll see why a heuristic isn't always good enough, and we'll build a true optimization model, And finally, we'll talk about how this same structure generalizes to a whole family of network problems. Every supply chain has to answer this exact question. Now, what is the transportation problem? At its core, it's a mathematical model for optimally scheduling the flow of goods from production facilities to distribution centers. This is a simplified figure with plants and warehouse locations only. The real supply chains will have many more stages, such as plants suppliers and suppliers suppliers and warehouses customers like retailers or other businesses. Picture the diagram on the left. On one side, you've got plants, Sunnyvale, Dublin, and Bangkok. And on the other side, warehouses, Amarillo, Teaneck, Chicago, and Sioux Falls. Every plant can ship to every warehouse, and each of those arrows basically carries a cost. Each plant can only make a limited amount, and each warehouse needs a certain amount. And the whole game, is deciding how much flows along each arrow to meet every warehouse's demand at the smallest possible total cost. And think about how common this is, a manufacturer delivering to regional distributors, a car maker supplying dealerships, basically any company with several sources and several destinations. All right, before we model anything, let's get the vocabulary straight, because every optimization model has, the same 4 pieces. First, parameters. These are the known quantities that describe the problem, basically the constants that don't change while we solve. Think how much it costs to ship a product from plant to warehouse, capacity of each plant, and demand at each warehouse. Second, decision variables, the unknowns the model solves for, like the actual decisions we get to make. For example, how many products we will ship from Dublin to Chicago. Third, constraints, the rules the solution has to obey, like not shipping more than a plant can produce or shipping more than demand at a warehouse. And fourth, the objective function, the single goal we're optimizing. We usually minimize cost-related objective function or maximize profit or coverage. In the transportation problem, the objective is to minimize the total cost, including transportation cost. Keep these 4 components in mind. We'll fill each one in. Okay, here's our example. The Pear Tablet Corporation. Pear makes tablets in 3 plants, Sunnyvale, Dublin, and Bangkok, and ships, to 4 warehouses, Amarillo, Teaneck, Chicago, and Sioux Falls. The goal is to minimize total transportation cost while meeting every warehouse's demand. Now look at the 3 tables. Production capacity, Sunnyvale 45,000, Dublin 120,000, Bangkok 95,000. Demand also in thousands, Amarillo 80, Teaneck 78, Chicago 47, Sioux Falls 55. And notice that basically total capacity of 260 exactly equals total demand. It's a balanced problem. And the shipping grid gives the cost per 1,000 units for every pair. For example, Sunnyvale to Amarillo is the cheapest at $250. And notice the costs aren't symmetric. Shipping out of Sunnyvale is cheap, while Bangkok, is expensive to basically everywhere because it's far from these US warehouses. Now, how do we actually solve it? One approach is a heuristic, basically a fast, reasonable rule of thumb. The greedy heuristic is the simplest. You always, allocate to the cheapest option available first. It's easy and it's quick, but here's the catch. The greedy solution may not be optimal. If we want a guaranteed best answer, we have to build a real optimization model, write it out mathematically, define those 4 components, and then hand it to a solver like Excel solver, CPLEX, Gurobi, or GAMS. Greedy is tempting because, grabbing the cheapest route each time feels obviously right. but cheap early can, well, force you into expensive routes later. We'll start with the greedy approach. Alright, before we start the greedy heuristic, let's define the heuristic in optimization context. In mathematical programming, finding the absolute best solution can require significant amount of time. When I say significant, for certain problems we need years to solve it optimally with the current supercomputers. Practically, they are impossible to solve complex problems. That is where heuristics come in. They are like smart algorithmic shortcuts. Most of the time, they do not promise to find the best answer, but they find a high quality solution quickly. So when exact solvers take years to run, heuristics basically give us a practical answer in short time. So the greedy heuristic for transportation problem is just like that. It gives us a fast, practical solution, but the solution may not be the best possible solution. Greedy heuristic uses a really straightforward strategy. Scan the cost grid, find the absolute cheapest route available, and ship as much as you can there. Then you cross off the plant or warehouse that is maxed out and just repeat the process. It is greedy because it only looks at the immediate best move and doesn't plan ahead for the global minimum. In this example, for the single cheapest cell is between Sunnyvale and Amarillo at $250. The rule says ship as much as you possibly can down that route, basically limited by two things: the plant's capacity and the warehouse's demand. Sunnyvale has 45 available, Amarillo needs 80, so we ship the smaller of the two, 45. That empties Sunnyvale completely and it knocks Amarillo's remaining demand from 80 down to 35. One route, locked in. Now Sunnyvale's tapped out, capacity 0, and it drops out of the running. We scan again, for the next cheapest cell among what's left, and that's Dublin to Teaneck at $990. Dublin has the full 120 available, Teaneck needs 78, so we ship, 78, the smaller number. Teaneck's now fully satisfied, demand goes to 0. And Dublin, still has 42 left to give. Okay, next cheapest available cell, that's Dublin to Amarillo at $1,280. Amarillo still needs 35 and Dublin, has 42 left. We ship the smaller, basically 35. Now Amarillo's satisfied, demand hits 0, and Dublin, is down to just 7 units of capacity remaining. See the pattern? Every single step we just take the minimum of what's left. Alright, keep going. The next cheapest open cell is Dublin to Chicago at $1,440. Dublin has just 7 left, Chicago needs 47, and we ship 7, basically the smaller number. Dublin's now completely empty, and Chicago's demand drops from 47 down to 40. 2 plants down, 1 to go, Bangkok. Now, only Bangkok still has capacity 95 units, and 2 warehouses still need product. Chicago wants 40, Sioux Falls wants 55. The cheaper of Bangkok's 2 options is, Bangkok to Chicago at $1,660. Chicago needs 40, Bangkok has 95, and we ship, 40. Chicago's satisfied now, and Bangkok, has exactly 55 left. Alright, last step. Only Sioux Falls is still unmet, it needs 55, and Bangkok, has exactly 55 left. The route is Bangkok to Sioux Falls at $1,730, and we ship all 55, Every capacity is now 0, every demand is met, basically the greedy heuristic is complete. Okay, let's tally it up. The greedy heuristic gave us 6 shipments. Sunnyvale to Amarillo 45, Dublin to Teaneck 78, Dublin to Amarillo 35, Dublin to Chicago 7, Bangkok to Chicago 40, and Bangkok to Sioux Falls 55. Multiply each quantity by its cost, basically add them up, and the total, comes to $304,900. Now here's the crucial question: is $304,900 actually the optimal cost? Greedy felt smart at every step, but well, remember, we only ever looked one move ahead, and that basically is Greedy's blind spot. Locking in cheap routes early can strand the expensive ones for the very end. Now watch this, let me propose a completely different plan. Ship Sunnyvale to Sioux Falls 45, Dublin to Amarillo 42, Dublin to Teaneck 78, Bangkok to Amarillo 38, Bangkok to Chicago 47, and Bangkok to Sioux Falls 10. First, check that it's feasible. Every plant ships exactly its capacity and every warehouse gets exactly its demand. It works, Now total the cost and it comes to $297,800, basically $7,000 cheaper than Greedy. And that well proves the point. The Greedy heuristic was not optimal. A cheaper plan existed. Greedy just couldn't see it. The key swap, was sending Sunnyvale's cheap output to Sioux Falls instead of Amarillo. A small reshuffle that ripples into real savings. Alright? If Greedy can't guarantee the best answer, what can? Well, a true optimization model. The recipe is exactly the 4 components we introduced earlier. Basically, lay the problem out mathematically, define your parameters, your decision variables, your objective function, and your constraints, and then, let a solver crunch it. A solver, searches feasible plan and returns the probably cheapest one. Something Greedy simply can't promise. In the next part, that's exactly where we're headed. We'll translate Pear's tablet problem into those 4 pieces and build the model formally. Under the hood, by the way, a solver like this runs linear programming. Thanks, and gig 'em.